I decided to go with the Business Intelligence Project. Space is one of my biggest interests, so I decided to find some data pertaining to SpaceX and their rocket launches. In particular, SpaceX has tried since its inception to create rockets that can land and be repaired for reuse. I figured that I could find data on this topic and use it to deduce any causal factors regarding the previous failure rate of this developing technology. Once I found a sufficient set of data, I copied and pasted it to Excel. There was an interesting variety of information pertaining to each launch from 2010 to early 2018. Things such as the booster version, payload mass, and launch site were just some of the information available. I wanted to use this data to find any similarities among the landing attempts that resulted in failure, as opposed to those which succeeded. To begin this process, I had to clean up some data. First, I did not particularly care about the mission outcome. All this column represented was whether the rocket reached orbit and deposited its payload, which could be a satellite, military technology, or supplies for the International Space Station. Nearly all of these were successes. What I really wanted to explore was the rate of successful landings and why any failures occurred when they did. So I went ahead and deleted the mission outcome column. Additionally, a few rows of data stated that there was no landing attempt made. I removed these rows as I was particularly looking into landing outcomes. Data of flights where a landing was never attempted would not be pertinent to my ends. Finally, I took the data from the landing outcome column and split it into two. The first column now simply stated whether the landing was successful, and the second detailed the type of landing attempted. This revision ended up making the graphical analyses much simpler. When I moved the data to Tableau, I started simple. I would compare the landing outcome with each of the other factors, one at a time, and look for any emergent patterns. Blue stood for successes, and orange represented failures. The first thing I discovered was when I compared landing outcomes with landing type. Ground pad landings had a 0% failure rate, which made it clear that those landings were not a cause of failure. Drone ship and ocean landings were mixed, while the two parachute landings both failed. While they both failed, I would not call parachute usage a reason for failure. There is a much clearer reason, which I will explain later on. After examining the pie charts on the left, I related the failure rate to the type of orbit each rocket was being launched to. No failures were seen for Sun-Earth orbit or Sun-synchronous orbit. The singular launch into polar orbit failed, while other results were mixed. While launches to polar orbit technically displayed a 100% landing failure rate, there was only one data point involved, so it likely could not be a causal factor. Next, I checked the average payload mass of the failed landings versus the successful ones. Interestingly, there is a significant difference here. I thought for a moment that I may have found an answer to my question. Heavier rockets were the cause of failed landings. But there were two reasons why that would have been incorrect. Firstly, payload to orbit is irrelevant to landings. Once the rocket reaches space, it gets rid of any cargo it brought with it. All that comes back to land are the now empty fuel tanks that were used to lift it up. Essentially, the weight of the landing components of a rocket remains the same, regardless of its payload mass upon launch. The other reason why this difference in averages had to be discarded was that on further analysis, I found that two data points amongst the successes were outliers, with payload masses of 4 to 5 times the normal amount. This data was slightly skewed, so I continued to research. Soon later, I created my first dashboard. This one contained two of the graphs I've already discussed, failures by landing type and failures by orbit type, but brought one more into the picture. Failures by launch site was an interesting one. Here, I realized that every instance of a failed landing resulted from one of these two launch sites, CCAFS LC40 and VAFB SLC 4E. Things were now narrowing down. I decided to look at these two launch complexes, absent of the other two, in order to find any similar causes of failure. If there weren't any, then one might believe these two locations were inherently flawed, and they in themselves were the reasons of failed landings. However, that would not have made sense, given that launch locations are independent of the landing location. A claim that the launch location caused failed landings, when landings often take place at alternate locations hundreds of miles away, would not have been accurate. I delved into further detail, filtering my data by the launch sites and analyzing other details in turn. What I quickly found is that roughly 3/4 of the failed launches occurred on two booster versions. This was significant data. It showed that nearly every failure resulted from only two booster types. However, my first thought was, wait, if there are only a few booster types used overall, in both successes and failures, this data is irrelevant. It would be like saying anyone who breathes dies, so breathing is the cause of all death. This might be meaningful if only a few people breathe, but everyone does. There is no current alternative. So that statement could never be true. Likewise, the idea that these two booster versions were causes of failure would rely on there being alternative types in use, rather than only the two. As it turned out, there were many other alternatives in use. Sorting landing outcomes by booster versions resulted in this chart. F9 v1.0 and F9 v1.1 were involved in the vast majority of failures. Two other versions also failed, but only one of each. Meanwhile, there were many other booster versions that succeeded. While many on this chart simply say F9FT, their names are shortened. Every individual circle of the same color represents a unique booster version. This visual made clear to me that these two booster types were major factors involved in failed landings. Next, I looked into further detail regarding these two booster types. I primarily wanted to see how many were used, how many failed, and how long they were used. While a few examples of F9 v1.1 exhibited successful landings, the majority did not. 7 total failures occurred between the two versions. Additionally, there was no column for 2017 or 2018. This I initially thought was a mistake, and I tried to fix it. Many of the launches from my dataset had occurred in 2017 or later, so I was confused why they did not appear. After a quick look, I realized that these booster versions were discontinued after 2016 and replaced by others. Now, I was curious whether the success rate improved following the implementation of alternative, more advanced booster versions. If it did, my already supported hypothesis that these two booster types were causes of failure would be strengthened even further. Sure enough, the landing success rate skyrocketed in 2017. There were 15 successes and 0 failures, as opposed to the previous high of 5 successes and 3 failures in 2016. Knowing that the problematic boosters were discontinued in 2016, this graph becomes far more meaningful. 2017's new booster versions bolstered the success rate to 100%, ending the regular failures of earlier iterations. In the end, I had my answer. Early booster versions were the primary factor of failed landings. This makes perfect sense actually. Initial prototypes are always more likely to fail. Now, I wonder whether I really needed to do all this data analysis to reach this conclusion. Maybe, maybe not. While I might have predicted this conclusion without using Tableau, I really did gain something from this project. I learned that you feel pretty damn sophisticated when you make charts in this app, even if they don't always mean a whole lot. For visual reference, this is a failed landing, if you didn't already guess as much. Now, a successful one. We'll end on a good note. Just kidding, let's end on a bad note.